Hello everyone. Today our team is going to present our final challenge, Learnable Butterfly Matrices for CNNs. To tackle this comprehensive challenge systematically, we have divided our project into 6 tasks, and member A was responsible for the foundation of the project, implementing the core butterfly layer with a custom backward pass, handling padding logic, depth multipliers, and gradient verifications. Member B took charge of task 0, evaluating how the network learns classical fast transfers. Uh, specif- Specifically the Hadamard and DCT matrices, and visualizing them via heat maps. Member C handle task 1.1, generating the random butterfly feature bank for CIFAR10, performing features standardization and setting up baselines. Member D executed task 1.2, implementing the attention feature selector utilizing soft-gate and straight-through tabulation mechanisms. Member E managed Phase 3.1, conducting the fashion MNIST CNN experiments across dense, fixed, learnable, and stacked butterfly configurations. Finally, member F closed the pipeline with phase 3.2, executing the CIFAR10 CNN experiments to analyze for architecture performance. To fulfill the project requirements of supporting non-power of two channel configurations, we successfully integrated a boundary safe padding workflow. The next power of two function uses low overhead bitwise operations to compute the target grid size P instantly. During execution, inputs are zero padded to P prior to the butterfly factors and then cleanly trimmed back to the original channel dimension C via the trim2D function. This dynamic encapsulation guarantees shape integrity and prevents any edge case boundary errors when processing arbitrary channel sizes, such as C equal to 50. And here's our core routing matrix generated by this function. At each factoring stage L, it structuralizes the index matrix where paired nodes are exactly separated by a straight distance of 2 to the power of L. By looping through the depth multiplier parameter D, our grid can sequentially stack multiple log factor matrices. This allows subsequent CNN blocks to dynamically unroll deeper, higher capacity representations, such as D equal to 2 or 4, without altering the underlying operator logic. And this is the custom backpropagation core of part A. In the forward pass, instead of allocating a massive computational graph for row slicing operations. We fetch indices efficiently using index sled and map our primitive 2 by 2 blocks sequentially. All intermediate activation stages are compressed into a clean stacked sensor intermediate before being saved. This custom management optimizes our VRAM footprint during deep bed propagation passes. In the backward pass on the next slide, we unroll the factors in reverse order. Crucially, to accommodate batched CNN feature maps, we leverage port sum to explicitly aggregate parameter gradients across both the batch dimension B and O spatial locations. This exactly matches our theoretical multi-variable chain rule deviations shown on the right. And finally, our empirical matrices provide undeniable validation of our layer's mathematical soundness. First, our parameter checker confirms a perfect match with the sparse complexity bound of 2C log 2C dot D across all test sweeps. Second, our analytical backward pass yields a yields a relative gradient error of exactly zero when verified against PyTorch native autograd. When evaluated against double-sided numerical finite differences, the error converges tightly around 10 to the power of minus 11, sitting comfortably near double precision machine limits. All shape and gradient tests have successfully passed, validating that our custom operator is exceptionally stable and fully prepared for deep CNN block integration.
Okay. Okay, so I'm going to present part B of our project, which is classical transform learning and verification. First, we'll look at section 01, which is what I implemented. I created a synthetic data pipeline where the input x follows a normal distribution and the target labels y equal a times x. For our target matrices, I generate 64 by 64 exact mathematical matrices as our ground truth transforms. I set the base step multiplier d to 1 and build the quantitative evaluation metrics and visualization tools. Next, in section 02, uh, we'll look at the training configuration. For the dataset allocation, I used uh, 16,384 training samples, 2,048 validation samples, and 2,048 testing samples. The problem dimension n is fixed at 64. We use the Atom optimizer and MSE laws to train the models. The butterfly architecture is tested with a depth multiplier of d equals to 1. And we compare random initialization against identity initialization. Next page. In this page, we will see the result for the Walsh-Hadamard transform. First, we look at the training loss convergence graph on the top. The blue dashed line shows the dense baseline, and its loss successfully converged to around 10 to the power of minus 13. The yellow line shows our butterfly model with d equals to 1. As you can see, it achieves the exact same extreme precision in the middle of the training. However, there's an interesting late-stage bounce after epoch 110, where the loss suddenly goes up. This is because of numerical inst- instability or floating point drift in our custom backward pass when the gradient becomes near zero. If you look at the heat maps below, the true Hadamard matrix, the learned dance matrix, and the learned butterfly matrix look almost identical. They all show a beautiful clear checkerboard pattern. Next page. And next, we'll look at the DCT2 transform result. Here, the story is completely different. If you look at the loss graph, the dense baseline still converges perfectly to around 10 to the power of minus 13. However, the butterfly model completely fails to learn, and it stalls horizontally at 10 to the power of 0, which is 1. And why does this happen? The potential reason is that a standard single-stage butterfly grid with d equals to 1 lacks the bit reversal permutations and diagonal scaling that are necessary to factorize a DCT2 matrix. Therefore, the true DCT matrix lies completely outside the representation space of this sample butterfly network. This is also very clear in the heat maps. The true matrix and dense matrix show wave-like patterns, but the learned butterfly matrix looked messy and gray because it could not align with the target. Next page. In this page, we have a summary table showing the performance and resource efficiency metrics. For the Hadamard transform, both models perform very well. The dense baseline has a test error of 9.81 times 10 to the power of minus 15, and the butterfly model has 4.25 times 10 to the power of minus 8. The matrix reconstruction errors are also very low. However, for DCT2, we can clearly see the failure of the butterfly model. The dense baseline achieves a test error of 8.75 times 10 to the power of minus 15, while the butterfly model's test error is very high at 0.885, and its reconstruction error is 0.95. This quantitatively proves that a D equals to 1 butterfly layer cannot handle the DCT transform. Next page. And finally, we'll discuss the core question of Tech Zero. First, which transform is learned more easily and accurately? The answer is Hadamard, because a recursive structure naturally matches the butterfly grid network. Second, do the learned models preserve the property of orthogonality? The answer is yes. Specifically for the butterfly model because its structural design naturally enforces mathematical orthogonality. orthogonality. Third, what happens if you use identity initialization? Our experiments show that it hurts convergence for tech zero. It locks the weights too rigidly at the start, making it hard for the optimizer to escape. Lastly, what happens if you increase the depth multiplier to 2? The answer is that the expressivity of the network increased drastically. This extra capacity will allow the butterfly model to successfully learn more complex transforms like DCT2. Next page.
Okay, so I'm Posse, and my text is random butterfly feature bank. Instead of training butterfly matrices, we use fixed random butterfly transform to generate high dimensional features from CIFAR 10 images. These features will then be used by the attention-based feature selector in Part D. And next slide, please. Next slide, please. With the previous one. Uh, okay, so, but, wait, next slide, please. Sorry. Butterfly metrics perform hierarchical pairwise mixing, reducing the computational complexity from the the one I show it on the right side of the PowerPoint. And each 2 times 2 block is initialized as a random rotation matrix, and the butterfly transform remains fixed throughout the training process. Okay, next slide, please. Since butterfly transforms are defined on power of 2 dimensions, the flattened image is padded from 3072 to 4096 dimensions. 4 independent random butterfly transforms are then applied. Finally, all outputs are concatenated into a 16384 dimensional feature bank. And next slide, please. Next slide, please. After generating the feature bank, we standardize all features using the mean and standard deviation computed only from the training set. So, so we prepare these. Finally, so we prepare 3 baseline raw pixels, the 4 butterfly feature bank, and a random feature subset, which serve as reference for the attention-based feature selector in Part D. And that's my part. Next slide, please.
Oh, okay. For Part D, my goal was to perform attention-based feature selection on random butterfly features generated from Part C. The input features were already extracted and standardized in Part C. Each image was represented by a random butterfly feature vector with dimension n equals r times n, which is 4 times 4096. So the 4 feature dimension is 106. 63,000, 16,384. In this part, I implemented an attention style type K feature selector. The selector learns one score from each feature coordinate. These scores are converted into gates using a sigmoid function with temperature. The gated features are then passed into a linear classifier. The training loss contains 3 parts: the cross and entropy loss for classification, a budget loss that encourages the total gate value to be close to k, and a binary loss that encourages the gates to move toward 0 or 1. And I evaluated for baseline raw pixels, all random butterfly features, random subset, and the attention selected subset. For the selected feature experiment, I tested k equals 128, 256, 512, and 1024. And next page. This figure shows the test accuracy as a function of the number of selected features k. The blue curve is the attention selected top k subset. The orange curve is the random subset baseline. The horizontal dashed line is the classifier chain on all random butterfly features, and the dotted line is the raw pixel baseline. The main observation is that the attention style selector outperforms the random subset baseline for every k. This means the selector is not just choosing arbitrary features. This is learning a more informative subset of a random butterfly feature. The best result occurs at k equals 512, where the test accuracy reaches 40.38%. This uses only 512 out of 16,384 features, which is 1/32 of the 4 feature dimension. Another interesting result is that the 4 random feature model achieves 36.83%, while the raw pixel baseline achieves 37.26%. So the 4 random feature bank by itself doesn't clearly improve over raw pixels. However, after feature selection, the selected random butterfly features outperform both baselines. And next page. The slide analyzes what the selector actually learned. On the left side of each pair, I show a histogram of the learned gate values. Ideally, the mask becomes strongly binary. We would expect most gates to be close to either 0 or 1. However, in my result, the gate remains soft. Most gate values are small and continuous, rather than close to 1. This means the learned mask didn't become strongly binary during training. Therefore, the final hard subset was obtained by ranking the learned scores and taking the top K features, rather than by directly thresholding binary gates. On the right side of each pair, I show how many selected features came from each of the 4 random butterfly transforms. The selected features are distributed almost evenly across the 4 transforms. For example, when K is 512, each transform contributes roughly around 128 selected features. This suggests that the selector doesn't concentrate on the specific transform. Instead, all 4 random butterfly transforms contribute useful feature coordinates. And next page. To summarize, the attention selected random butterfly features outperform raw pixels with all feature baseline and random subsets. The best result is that k equals 512 with 40% test accuracy gives a 32 times reduction in inference time feature dimension. The accuracy improves from k equals 128 to k equals 512, but slightly drop at k equals 1024. This shows a trade-off. Using more features can provide more information, but after some points, additional features may introduce noise or less useful coordinates. The selected features are distributed evenly across 4 random butterfly transforms, so no single transform dominates. The learned gates remain soft rather than binary, so the final feature subset is selected using top K score ranking. Based on these experiments, random butterfly features appear to be useful as a fixed feature map only when combined with feature selection. The 4 feature bank contains many noisy coordinates, but the selector can inject a more informative subset. Okay. For the last question, for last question, if a butterfly transform were also learnable, the main focus will change. In my current experiment, the butterfly transform are fixed and random, so the main problem is feature selection. But if the butterfly transform become learnable, then the problem becomes feature learning plus feature selection. We should focus on whether the learned butterfly transform can produce more case-specific features for Cypher-10, and whether this reduces the need for aggressive feature selection. The important comparison would be fixed random butterfly versus learnable butterfly under the same K and similar parameter budget. We should check whether the accuracy gain is worth the extra trainable parameters, training cost, or possible hourly. Okay, this is it. The end.
Okay, my part is part E, the fashion and an IST CNN experiment. The goal is simple. I test whether the normal dance one-by-one convolution in the CNN can be replaced by butterfly mix. I compare several variants, dance baseline, fixed butterfly, learnable butterfly, and stepped butterfly. The main question is whether butterfly mix can keep good accuracy while using fewer parameters. Next page. For the model, I used Fashion NNIST, which has 28 by 28 grayscale image and 10 flashes. The CNN is a small mobile style network. It has convolution layers, 2 blocks, global average pooling, and a final linear classifier. The important part is inside each block. Each block has a test-wise convolution and a channel mixing layer and dash normalization and value. In this experiment, I only changed the channel mixing layer. For the dense baseline, I used the normal one-by-one convolution. For the butterfly models, I replaced it with butterfly mix. Next page. In this experiment, I compared 5 models. The first model is the dense baseline. I used the normal one-by-one convolution for channel mixing. The second model is fixed butterfly and d equals 1. It replaces the one-by-one convolution with butterfly mix, but the butterfly parameters are frozen. The third model is learnable butterfly and d equals 1. It also used butterfly mix, but this time the butterfly parameters are trainable. And I just stacked butterfly models with d equals 2 and 4. These models use deeper butterfly products to increase the expressiveness of the channel mixer. All models use the same dataset, the same CNN architecture, and the same training setup. The only main differences is the channel mixing layer. Next page. This slide shows the main result. The dense baseline reached 84.67% test accuracy with 25,546 trainable parameters. The best model was the stacked butterfly model with d equals 2. It reached 87.21% test accuracy with 22,602 trainable parameters. This is important because it means the d equals 2 butterfly model achieve higher accuracy than the dense baseline while using the fewer trainable parameters. We can also see that d equals 2 didn't improve over d equals 2. So increasing the butterfly depth helps up to a point, but making it too deep doesn't necessarily give better performance. Next page. This slide compares the accuracy of the butterfly models. On the left, the validation accuracy curve shows that the d equals 2 stacked butterfly model reached the highest validation accuracy by the final approach. On the right, the test accuracy as a function of d shows the same trend. When d equals 1, the accuracy is low. When d increased to 2, the test accuracy improved to 87%. However, when d increased further to 4, the accuracy dropped to 86%. This means that stacking butterfly factors helps, but only up to a point. In this experiment, d equals 2 gives a better accuracy. Next page. This slide shows the trade-off between test accuracy and the number of trainable parameters. The dense baseline has 25,546 trainable parameters and reach 84% test accuracy. The stacked butterfly model with d equals 2 has fewer trainable parameters, but reach a higher test accuracy of 87%. This shows that butterfly mix can be a good replacement for dense one-by-one convolution on fashion and an IST. However, D equals 4 uses more parameters and take much longer to train, but it doesn't outperform D equals 2. So the best trade-off in my experiment is D equals 2. Next page.